All right, guys. Sorry. We have a kind of a blast from the past. We're doing some more derivatives. And these are the inverse trig derivatives. So if you remember from, say, pre-calc, you did inverse trig, arc sine, arc cosine, arc tangent, those guys. These are the inverse trig derivatives. So we'll derive one of them. I'll give you the rules for the rest of them, and we'll just see how to apply them. So let's start by remembering this theorem. This is the inverse function rule. If I want to take the derivative of an inverse function, I could do it by doing 1 over the derivative of the first, or the original function with the inverse function plugged into it. So let's look at this example for inverse sine. Remember, this is inverse sine. This is not 1 over sine, which we can also write as arc sine. These are the same thing. So here's how we're going to do it. We're actually going to rephrase it in terms of this function, of this rule. Let's see what happens. So let's write f inverse of x is equal to, and we'll call it y, is equal to arc sine of x. And this is just going to be helpful in a second to do a little kind of algebraic manipulation. So this is arc sine of x. And if you remember, what this means is the inverse of sine. So this is the thing that when I plug y into sine, I get x as an answer, which I can write down as this is equivalent to, what you do in math is these kind of weird arrow guys. This is equivalent to x equals sine of y, which we'll use in a second. All right, so now using our rule up here, f inverse of x, the derivative of that, I guess I wrote that wrong, but that's fine way to do it, is equal to 1 over. Now what do I need? I need the derivative of the original, right? Arc sine is the inverse of sine. So I need the derivative of sine, which is cosine. And then I also need f inverse of x, so this would be cosine of arc sine. Which is fine. This is a fine formula, but it's not particularly useful. We want to make it a little cleaner, and we can. How do we do it? Well, I can use the following fact. X equals sine of y. To make the substitution, this is equal to 1 over, we still have the cosine, we still have the arc sine, so the cosine, we still have the arc sine, but our x, right, x is sine y, so I can replace that with, I guess I'll do it in orange, sine of y. Sine of y. All right, and if you remember, since arc sine and sine are inverses of each other, they will cancel. So this is 1 over the cosine of y. 1 over the cosine of y. And now you might be thinking, well, this is a much better formula, but the issue is that I start with x's and I have y's in here. So I want to bring the x's back. So we use another trick. Let's remember that cosine squared of x plus sine squared of x is equal to 1. And since I have a cosine down there, I guess actually I mean cosine, doesn't matter what letters I have in here. So cosine squared of y plus sine squared of y is equal to 1. I can solve this for cosine, right? I can get cosine squared of y is equal to 1 minus sine squared of y. So cosine of y is equal to 1 minus sine squared of y. Right, I don't need plus or minus because I'm not looking for all solutions. I'm just looking for a solution. So that's a formula for cosine of y. So I'm going to rewrite this as 1 over square root 1 minus sine squared y. Right, which I could actually rewrite as 1 over square root 1 minus sine of y squared, right? Sine squared y is sine of y squared. But what is sine of y equal to? It's equal to x. So this is equal to 1 over the square root of 1 minus x squared. And there's our final answer. There's the formula that I want. What more can we do with this? Well, we can do really kind of anything. All these other, that's what I'm trying to say. All these other inverse trig functions, we would derive the rule very similarly. It would just apply tricks like this over and over again. So rather than boring you or perhaps confusing you by doing it, I'm just going to give you the formulas. So for arcsine, we just figured it out. This is 1 over the square root 1 minus x squared. And we note that x can't be plus or minus 1, because otherwise we'd have a 0 in the denominator. For arc cos, I guess I'll do a different color, we get negative 1 over the square root 1 minus x squared. Again, x cannot be equal to plus or minus 1. Right, so these two are very similar. The way I remember it is derivative cosine is like negative sine, so cosine's got the negative in there. Let me move this up a little bit. Arctan's a weird one. It's 1 over 1 plus x squared. So it's got a plus sign in there. And there's no restrictions there because that denominator can never be 0. Cosecant and secant follow the same kind of pattern as sine and cosine. Cosecant, however, is the negative 1. So this is negative 1 over, and here is where it gets really wild, the absolute value of x times the square root of x squared minus 1. And again, x cannot be equal to plus or minus 1, but also not 0 in this case, because then that absolute value would give us a 0 in the denominator. Secant follows the same pattern as sine and cosine. This will be positive 1 over absolute value of x, square root x squared minus 1. X cannot be equal to plus minus 1 or 0. And then cotan is just the negative of arctan. We'll do this one in, I guess, a bright blue. This is, cotan is negative 1 over 1 plus x squared. And again, there's no restrictions because 1 plus x squared can never be 0. Now, all right, you're like, Doc, you're the worst. 6 more derivative rules to remember. And of course, these are derivative rules. These are not integration rules. We'll get to those. But there's like five. There's like three, right? These two really are the same, just with a minus sign. These two really are the same, just with a minus sign. And these two really are the same, just with a minus sign. So you just got to kind of get all that straight in your mind. You're able to do it with trig in one direction, right? You know, the normal trig functions. You can do it with the inverse trig functions. So let's see how we put this all together. Well, let's calculate some derivatives, right? And we have to remember all our derivative rules from last year. So let's start with number one here. Number one, this is a polynomial times an inverse trig function. So I'm going to need the product rule, number one. So it's first times the derivative of the second. So using our new rules, this is 1 over the square root 1 minus x squared. First times the derivative of second plus second, I guess sine inverse of x, which is arc sine again, times the derivative of first, 2x plus 5. All right, so you got to remember sine inverse is the same as arc sine. They're the same function. And then, of course, we can simplify things here. X squared plus 5x plus 6 over the square root 1 minus x squared plus 2x plus 5 times arc sine. Okay, we can simplify, but we don't, there's not much more we can do besides that. All right, let's look at number 2. 2, if you notice, that's a function inside of another function, right? We are plugging cosine into arc cosine. So let's calculate that. Plugging a function into another function, we need a chain rule. So we do the derivative outside, but we leave the inside alone. So the derivative of the outside is negative 1 over square root 1 minus x squared. But of course, 1 minus x squared, it's taken up by cosine here, 1 minus cosine squared of x. And this is then times the derivative of the inside, which is negative sine of x. And you're like, okay, Doc, let's leave it like that. We'll call it a day. But we can actually do some simplification because remember, since sine squared x plus cosine squared x is equal to 1, sine squared x is going to be equal to 1 minus cosine squared x. So I can make some simplifications here. Firstly, the top's being multiplied here is going to be sine of x. That's the numerator of my fraction. And 1 minus cosine squared, we said, is sine squared. So this bottom is going to be the square root of sine squared of x, which is sine of x. The square root of sine squared is sine of x. And this is actually equal to 1. All right, and you're probably thinking, why didn't we see this why shouldn't we have seen this in the beginning? Well, if you remember, when I plug a function into its inverse, this is actually that g of x is going to be equal to x. The derivative of x is 1. So, 2 ways to get this problem. Here we go, number 3, h of x. So to do h prime, I've been lazy about writing my functions here, but h prime, we need a quotient rule. Quotient rule, low d high minus high d low. So this is going to be low, the inverse cosecant, d high, the derivative inverse tangent is 1 over 1 plus x squared. Low d high minus high, tan inverse x, d low. which is the derivative of inverse cosecant, which is -1 over the square root. The absolute value of the square root. Absolute value of x times the square root of x squared minus 1. Low d high minus high d low, all over low squared, which we would write as cosecant inverse of x squared. Again, there's another derivative just using our new rules. And now finally, which color do I want to do the last one in? Let's go for blue. Finally, L of x here. So we do L prime of x. L prime of x. So for this first guy, I got cotan to the third power. So I need a chain rule here. So this is going to be 3 cotan inverse of x squared, right? And then I multiply by the derivative of cotan inverse, which is -1 over 1 plus x squared. So chain rule for that guy. Plus, for the second guy, I'm going to need a product rule. But that's just regular secant, right? And the derivative of regular secant is secant tangent. So this is going to be x squared, first times the derivative of second, secant x tangent x, first times the derivative of second, plus second times the derivative of first. And there's our answer for number 4. There's our answer for number 4. I'll give you a moment to copy all these down. All right. Now, what do you have to do? You have 8 of these problems to do. So let me give you maybe some hints. 1, that's a chain rule. Chain rule. 2, we have a product rule. We have a quotient rule for that guy. This guy's also going to be a chain. This guy will be a chain. This guy will be, I guess there's a chain rule in there, just at the beginning here. Here for this guy, we have a quotient. And this last guy, we're going to have 2 chain rules. 2 chain rule. 2 chain rules. 2 chains rules? No. Yep, that's a terrible joke. It's fine. We need 2 chain rules there. So, good luck.